Okay, so here's where we were last time. We were talking about constrained optimization. So, an unconstrained optimization is an extremely familiar story. You take the gradient, set it equal to 0, worry about differentiability. These are your critical points. And it's just like in Calc 1. Constrained optimization, remember, is not a familiar thing, right? There is no Calc 1 version of this, because there's just not enough space in a one-dimensional domain to have this kind of a problem. Right? Okay, so we talked about single constraint optimization, the Lagrange multiplier theorem, and then here's what a two-constraint problem looks like. And just a reminder, we talked about all this last time, but there's a constraint equation, constraint gradient. Right? Here's our second constraint. Here's the constraint set. Here's the constraint equation and the constraint gradient. So we have two separate constraints, both of which apply on our actual total constraint set, which is the intersection. I mean, after all, if I have to satisfy both constraints, then I have to be on the intersection of the two individual constraint sets. Okay, so notice what we have here is a constraint set that is a curve. And we have these two constraint gradients that define a plane. Right? And so looking at this picture, what we're interested in, we talked through the details of this last time, when we can't rule out this point as a possible maximum, well, that's when the objective gradient is perpendicular to the curve, while both of the constraint gradients are perpendicular to the curve. The constraint gradients define this plane. Typically, as drawn here, for example, you would expect, in fact, for these two known vectors perpendicular to the curve would make the entire plane. All vectors that are perpendicular to the curve. So, if our objective gradient in purple, gradient f, if that is, in fact, also perpendicular to the curve, in other words, the case that we're interested in where we can't rule this out as a possible maximum, it's going to be a combination of these two constraint gradients, gradient G, gradient H. So that's our typical case. This is the what you might call the Lagrange condition for this two constraint Lagrange multiplier theorem here. And there's also some other conditions we have to worry about. Differentiability, of course. I mean, obviously this whole ruling out process relies on computing directional derivatives with dot products, and that requires differentiability. So if that fails, we're in trouble. And then also these cases here, these are the different ways in which these two vectors might not actually span an entire plane. Right? So what if they're parallel to each other? Or what if one of them is 0 or the other one's 0? Either of these things would mean that, I wouldn't actually be spanning an entire plane. I would just span a line, and my ruling out process would fail. Okay, so all that discussion. Here is our theorem. More to the point, here are the three different conditions we have to check. We have to look for points where f is not differentiable. We have to look for points where one of these degeneracy conditions might come up. And we have to look for points where the Lagrange condition is satisfied. Any of those happens, we've got ourselves a critical point. Said differently, if any one of these three things happens, then we have a point where we cannot rule it out with our kind of simple-minded rule it out process. We'll look at the functions obviously increasing, that kind of thing. Okay. All right, so let's see an example. Here we go. We want to optimize this function right here. There's our objective function. And our constraints are, we're only interested in points that are on that cylinder and that plane. So two constraints. So let's play the game. Step 1, looking at our objective function. Is there any point where this fails to be differentiable? No, it's a polynomial. Polynomials are differentiable everywhere. So no critical points from differentiability. Next, we have to look at degeneracy. Well, now, okay, so this cylinder gives us this constraint function, which gives us that constraint gradient. This plane gives us this constraint function, which gives us that constraint gradient. So we've got to look at these two constraint gradients, and we've got a list of several questions we have to ask about them. Right? Let's go back up here to our theorem. Here's the three different questions we have to ask. Is either one of them ever zero? And then finally, is one a multiple of the other? Okay. All right. So let's start with the easy one. Is gradient h ever zero? No. 1 is never 0. I don't care what x is. All right, so that's pretty okay. Second, and a little tricky, is this ever 0? And it's tempting to say yes. It's tempting to say, oh, well, look at this. All I would need is for x and y to equal to 0, and I've got that gradient of g would equal to 0, and aren't those going to be critical points? It's very tempting. Keep in mind, all of this discussion of, ruling out, we're only needing to rule out points that are actually in contention anyway, right? So we're only interested in points that satisfy these two conditions. So the thing is, any point that would make this gradient gradient of g equal to 0 would not be on the first constraint. It would not satisfy x squared plus y squared equals 1. So this is, again, you got a heads up for this kind of thing. If you list, the origin as, oh, hey, that's, every point on the z-axis, in fact, because, look at this, degeneracy, then you're not paying attention to the constraints. Is everybody on board with that? Okay. All right, last question. Now I've got this listed as gradient of g is a multiple of the gradient of h. It's actually not important which one's a multiple of which other one, right? If either of these vectors were the 0 vector, we would have already declared degeneracy and not need to worry about that one anymore. So when I'm checking this third degeneracy condition, feel free to entertain the question of, is either one a multiple of either one? And the temptation to say, well, it's just a k versus 1 over k. What's the difference? Well, the difference is, what if k is 0? Okay, so let's think about how that applies to these two gradients. Now I could, as listed, I could ask, is this ever a multiple of that? And, well, if I'm going to multiply this times some k and have it equal to this, I could, this is possible, right? Because look, k would just have to be something I can multiply by 1 to get 0. So k would have to be 0. And then you can take it from there, see what that says about x's and y's. And you won't find any, of course. But look how easy it is if you just consider the question the other way. Let's ask, can I multiply this times something to get that? And now that third component question becomes, is there anything I can multiply times 0 to get 1? And, well, no. End of discussion. Right? So you're welcome to go either way, and in either case, whichever one you try to find to be a multiple of the other, it's not like you're going to get different critical points or something. Right? So feel free to do it whichever way you like, but I encourage you to look for the opportunity to make your argument as short as possible. And this is nice. Let me pause for a moment for questions about that. How are we doing? Everybody happy? Okay. All right. So we have not found any critical points so far. And again, you can decide for yourself, is that good news or bad news? Okay, now, lastly then, our last source of critical points, the Lagrange condition. Now, here it really does matter which vector is a combination of which other vectors. You can't say, you just got to be careful. You can't say, look, I'm going to ask if maybe gradient of g is a linear combination of gradient of f and gradient of h. Nope, that's not okay. Which vectors up here are considered in the degeneracy, it's always the constraints. And which vector needs to be a combination of the constraint gradients? Always the objective. So that's strict. No flexibility. So anyway, let's write down what these gradients are in this example. Here's our objective function. The gradient's easy to write down. Our constraint functions, their gradients we've already written down. And the Lagrange condition gives this vector equation, which of course, if you look at one component at a time, gives us these three equations. Now, again, usual, just like in the single constraint case, if you look only at those three equations, you don't have enough information. You've got 5 unknowns: x, y, z, lambda, and mu. But of course, we're only interested in the Lagrange condition as it applies to points that satisfy our two constraints. So don't forget to write down the two constraint equations as well. And now grand total, we have 5 equations and 5 unknowns. And, we sort of optimistically hope that maybe we can solve this. Let me remind you, the algebra on these can get out of hand. And that's mostly my problem because I have to write exam questions where the algebra is, not outrageous. It's really easy to write an outrageously difficult question. I got to be careful not to do that. But also not just painfully trivial and identical to all the algebra you've already done. Right? To come up with a sort of a different, appropriate question is tricky. So that's arguably good news for you, because most of the questions that you'll see then will algebraically be, not terribly different from something that you've already seen. And so there's this example here. There's some examples in the exercises. Pay careful attention to how the algebra works out. What is the strategy in each of those cases? What kinds of things should you notice, right? And if you can do all of those, and if you're comfortable with those ideas, then you should be in good shape for what you'll face. But do be aware, in life, sometimes the algebra that you get down to here is intractable. Okay, so here we do. What do we do in this case? Where's our foot in the door? And the foot in the door is that equation right there that immediately tells us mu is equal to 1, which I can then plug in there and there. And we just eliminated one of the equations and one of the variables. And now instead of 5 by 5, now we have 4 by 4. Everybody see what happened there? So always look for that foot in the door. It's just nice when it happens. Okay. So here's the remaining 4 equations. And we're going to do what we did previously. We're going to eliminate lambda. I'm going to solve for lambda. The two different things that lambda is equal to have to equal to each other. And that tells me x is 2y. Anybody see what happened there? Okay. This x equals 2y, I can then plug into there. And now I know y. Once I know y, I know x. Right? And so you can just kind of wiggle your way through the algebra until you get everything that you need. Now that I know x and y, plug into there, and I can get z, which gives me the points. Okay, so that's how it works out in this case. Again, not every example will play out exactly like this, but this is one of a handful of reasonable scenarios. Okay, everybody happy? So real quick before we go on to the next thing, I'll point out that this two constraint Lagrange multiplier theorem, it's different than the single constraint, but it's arguably not terribly different. In fact, notice inside of this two constraint Lagrange condition is what is exactly our original single constraint Lagrange condition. It's basically we're noticing that there's a sort of a pattern that's continuing here. You could probably even guess what would happen if instead of 3 variables with 2 constraints, what if there were 4 variables, and thus I couldn't begin to draw the picture, but what if there were 4 variables and 3 constraints? Well, you just, as it turns out, you just have an extra term. You'd have a third term in your Lagrange condition. And you'd have to consider other ways that the 3 constraint gradients might, there might be some unfortunate coincidence of one of them 0 or one of them the combination of the others or something like that. Okay. All right. Okay. So moving along to the next section, we're going to talk about global extrema. This is, if you get right down to it, ultimately what you are really kind of interested in with optimization. If you think about it, if you're a small business owner and if you're trying to maximize profit, and if you were to find a local maximum of profit, right? That local maximum, okay, so, from this local maximum, any parameter that I change in my business plan, this is the best profit that I can make with nearby parameters. Well, yeah, but is there some dramatic change that I could make in my parameters for my business plan that might give me more profit? Of course, you're very interested in this question, right? So local maxima, it's okay. I guess it's the first step, but we want global maxima. Right? If you're trying to maximize profit, or if you're an engineer and you've got various tweaks that you can make on your engine design, and you want to maximize efficiency. What's very interesting to note that, we're at a local max of efficiency, but a dramatic change, go way over here, we get a significant increase in efficiency. Also very interesting. Okay, the problem with finding global extrema is this word global. Just a very sort of broad brushstrokes, sort of philosophically, if you will. Derivatives, well, let's be more broad. Calculus, right, is about local stuff. Derivatives are all local. It's telling you what's happening nearby. So you can see how derivatives would help us identify local extrema because calculus studies the local. How are we going to get our hands on the global, right, with just calculus? So it's a hard problem. There's a couple of components of this. The first component that I want to talk about is basically how to break up a domain into pieces. I'm going to talk about subdomains. And I don't want to, let's not get rigorous about exactly what we mean by sub. You'll see the pattern once we get to it. But a subdomain inside of a domain is a collection of points that all have the same constraint equations. So, for example, let's look at this closed unit ball in R3. So we've got this solid closed unit ball. There's an inside and there's a surface. And both of these are what I call subdomains because this inside, all of the points that are in the interior of this solid ball, all of those points have the same constraints, namely none. There are no constraints. Every vector is a tangent vector, and so this condition satisfied. On the other hand, let's look at the surface. Well, this surface, also a subdomain by this definition, because all the points on that surface are subject to the same constraint equations. Namely, there is a constraint, and the constraint is x squared plus y squared plus z squared equals 1. Okay, so a whole domain you can break up into subdomains in this way. And then here's the argument we take from there. Let's look at this case, and this is a nasty case right here. Let's consider, if our domain is the solid closed unit square in R2. So all of this, right, this whole thing. I can break it up into subdomains. Here's how I would do it. I'm going to consider the interior. I'm going to consider this edge, and that edge, and that edge, and color choices. Oh, fine. This edge. All of these are subdomains. For example, this green edge over here. Every point on this green edge has the same constraint equation. Okay. X equals 1. Any point on here, the only constraint on that green set is x equals 1. Likewise for the others. But awkwardly, there are also these 4 points. These individually are their own subdomains. And this is annoying because, from this point, if I'm interested in, okay, what are the allowable tangent vectors? From this point here, the constraint x equals 1 is not the only problem that I have. I also have to worry about the fact that it's on this edge too. Right? So you have to treat this separately. So technically we have 9 subdomains. Yikes. Here's the idea though. We're interested in the global maximum. Right? The global maximum, I don't know where it's going to be, but I do know it's going to be on one of those 9 sets. That much is clear. So now let's think a little bit further. Imagine this global maximum that we're looking for, and let's suppose momentarily that global maximum is in the interior. Well, if it's a global maximum, and if it's in the interior, guess what? It's also a local maximum in the interior, which means it will be a critical point in the interior. And so if I were to just forget about all the other subdomains and just think about this one subdomain and just play the critical point game as is appropriate to the constraints for this subdomain. Write down all my critical points. The point I'm looking for will be one of them. Now, of course, that's not the only possibility. It is also possible that our maximum, our global maximum, will be on that different subdomain. Well, but if it's a global maximum everywhere, then it's also got to be a local maximum on this subdomain. So if I write down all the critical points on that subdomain and consider all of them too, the global max that I'm looking for will be on my list. So look, this max, where it's going to be, I don't know. But if I were to consider each one of these subdomains separately, write down all the critical points for all 9 of these subdomains, the global maximum's got to be on that list. Right? How we doing? Everybody on board? Okay. So the nice punchline to this is that if you're looking for global maxes, break up your domain into subdomains, and just, you've got several little local max critical point searches, and that's it. Very nicely, by the way, notice we don't even need a second derivative test. If the global max exists, it's got to be on this list of critical points. It's going to have the biggest value of the function of all those critical points. So just list all the critical points. See the values of the function. Compare. And it'll fall right in your lap. So that's the big idea. Now, there is one thing that I swept under the rug in this discussion. I made an assumption that's appropriate in this case, but not always appropriate, and furthermore requires discussion. I asserted that the absolute maximum point exists. And how do we know this? Maybe there is no absolute maximum point. For example, let's go back to Calc 1. Here are some pictures of scenarios where there is no absolute maximum value. Right? If your domain has if the function has a discontinuity in your domain, you could have a function that looks like this, and there is no point in this domain that achieves an absolute maximum value. There is no absolute maximum value for this function. So there is no maximizer. Likewise, if your domain is open at one end, even without a discontinuity, there's still no maximizer. If your domain is not bounded, then even though there's no open endpoint, even though there's no discontinuity, but we've got an unbounded domain. We could just take off and start running and let the function keep getting bigger and bigger. No maximizer, right? So there's various different ways in which it could very plausibly be the case that there, in fact, is no absolute maximum value for the function. And if there is no absolute maximum point, don't try to find it. Right? It's a wild goose chase, they call it. Okay, so before we start playing games with subdomains and critical points and comparing, let's make sure that the thing we're looking for exists. Otherwise, we could end up in the following silly situation. I'm going to show you a Calc 1 version. Suppose I consider a function defined on the entire x-axis, so unbounded, right? And here's my function. The function is f of x equals x cubed. Let me write that down. F of x is x cubed. And now, between us, I mean, we know this clearly. Look at the picture. There's no maximizer, right? The function gets arbitrarily large. There is no absolute maximum value, and therefore there is no point that achieves the absolute maximum value. But if I were to blindly play the game and start to say, look, I'm going to find all the critical points, I'm going to look at all the critical points, and I'm going to decide which one of these critical points has the biggest value, and I'm going to declare that to be the maximizer. Then I get a preposterous result, right? Because, and I'm going to do this in red to show the danger here. You take f prime, you get 3x squared. That implies, which I need to equal to 0. That implies x equals 0. Therefore, this is my only critical point. And here's a complete list then of all critical points and their values. Of all these values at all of these critical points, the largest value of my critical points, the largest value is 0. How silly would it be of me to declare this 0, x equals 0 to be the absolute maximum point for this function? It's garbage. Everybody see what I'm saying? Okay, so the argument here that, the maximizer's got to be on one of the... no, it doesn't. Right. So step one really is, let's try to figure out how to establish that the absolute maximizer in fact even exists. Once we know it exists, then it's got to be somewhere in the domain. Therefore, it's got to be on one of these subdomains, and therefore it's got to be a local max, and therefore it's got to be a critical point, and therefore our strategy works. Okay. All right. This is a hard problem. How do we know when an absolute maximum is going to exist? And so we're going to invoke a big theorem. This is a big theorem from analysis. And what it says, if you are looking at a continuous function, it's a big condition. Function's got to be continuous. If your domain is closed, remember we talked about closed at the beginning of yesterday's lecture. So all the boundary points have to be included in the set. And if the domain is bounded, you've got to be able to put a fence around it. Your domain can't run off to infinity in any direction. It's got to fit inside of some ball. So these are the three conditions: continuous, closed, and bounded. Right? The function has to be continuous. The objective has to be continuous. The domain has to be closed. The domain has to be bounded. If those three conditions are satisfied, then f does achieve an absolute maximum value somewhere in your domain. And then our problems are resolved, and we just proceed by the methods we just talked about. Come over here, bud. Okay. All right. Okay, so let's do an example. So, suppose I want to maximize this objective function, and subject to this constraint. That's a single constraint. Everybody happy? And by the way, notice that's an equality. That's equal. That doesn't say less than or equal. So, in fact, this domain has but a single subdomain. It is its own single subdomain. Every point on this ellipsoid is subject to exactly the same constraint equation. Okay. In fact, you may recognize this is a question we've already looked at. We considered that function, that constraint. We did the whole Lagrange multipliers thing. This is the one where you had to worry about, don't inadvertently cancel zeros. Right? Dividing by zero, dangerous, right? So the punchline was that we had 6 critical points. That we didn't know what to do with those 6 critical points at the time. We just said, well, here's my 6 critical points. Now we know what to do. We know that this function is continuous. This domain, it's an ellipsoid. It is closed. It is bounded. Just got to think it through. Right? So we know the absolute maximizer exists. We know, therefore, one of these points has to be the absolute maximizer. Therefore, I take these 6 points, I plug them into my function, and I look at these values. And again, we know the maximizer exists. We know it's one of these points. Therefore, we know one of these 6 values is the absolute maximum value of the function. And well, again, at this point, it's pretty clear. 36 is the biggest number on this list. So 36 is the absolute maximum value of the function. And these are the 2 points in the domain that achieve that absolute maximum value. Everybody happy? All right. Now, this was an easy one because, for one thing, there was only one subdomain. And for another thing, we already did most of the work in finding the critical points. Okay. All right, so here's another one. Let's consider this objective function defined on the closed unit ball in R3. Now, the closed unit ball, let's think about that. That closed unit ball, it's a solid, remember. Balls are solids. Sphere is a surface. Ball is a solid. Okay? So in terms of subdomains, well, there's the interior. The points in the interior have no constraints. And then there's the boundary, the points of which have a single constraint, namely x squared plus y squared equals 1. So step 1, we've got to take this domain, break it up into 2 separate subdomains, on each of which we have a separate optimization problem. Okay, let's consider the unconstrained interior. In there, we're going to take the gradient set it equal to 0, but the gradient is 1, 2, 3. So, where is the gradient equal to 0? Never. Okay, so that was an easy one. The interior resolves very nicely. There are no critical points in the interior. Quick pause. Everybody on board so far? Everybody's good? Okay. All right, next. Now, having considered that interior, now I do also have to consider the boundary. On the boundary, there is a constraint. The constraint is that this function has to equal to 0. Right, my constraint equation is x squared plus y squared plus z squared equals 1. Therefore, this function, x squared plus y squared plus z squared minus 1, has to equal to 0. There's my constraint function. It's a single constraint problem. So here's my constraint gradient. I'm sorry, I skipped a step here. There's my constraint gradient. There's my degeneracy condition that I need to worry about. Can this ever happen? Could the constraint gradient ever be 0? Well, kind of, but not really. Right? We've seen an example like this before. If the constraint gradient were 0, I would need x, y, and z all to be 0. But if x, y, and z are all 0, then this condition is not satisfied. Yeah? Everybody happy? Let me write that a little bit differently. This and this are incompatible. So no degenerate critical points. Pause for questions. Is everybody good? Okay, next, let's look for the Lagrange critical points. Here's our constraint gradient. Here is our previously computed objective gradient. This then is the Lagrange condition. Don't forget, we also have the constraint itself. Therefore, here are our 4 equations and 4 unknowns, and so it begins again, right? We've got this, system of equations. How do I go through and solve this 4 by 4 non-linear, in this case, right? Highly non-linear system of equations. And in this case, look, it works out really well, just like it did before. Step 1, eliminate lambda. Solve for lambda in terms of x, y, and z. Those things that you get all equal to each other, that tells you these relationships between x, y, and z. Next, put those into your constraint equation, which becomes this, which of course is that. Which makes this easy to solve for x. Right? X has got to be plus or minus square root of 14. Once you know x, you know y, and you know z. So this little algebraic process is just like a previous example that we did. In this case, the details are different, but it's morally the same. Yeah? Okay, so, yeah, 2 critical points. By the way, up here, let's see, let's go up to here. Yeah, this closed unit ball is closed. Right? It's bounded because it is a ball, therefore it's inside of a ball. And this function is continuous because it's a polynomial. So we know the absolute maximum exists. These are the only 2 critical points, so we know the absolute maximum is one of these. We compare the values. That's the maximizer. How are we doing? Everybody happy? Okay. Right. So I'm going to do one more example. I'm not going to do the whole example. I just want to show you sort of how to break things up. This is that scary square that we were looking at that had 9 subdomains. Right? And I just want to show you how that sort of works out in practice. So here we go. There's my unit square. And let's look at this function. Let's try to find the absolute maximum value of this function on that unit square. Well, continuous, closed, and bounded. No problem. We know the absolute maximizer exists, so let's take a deep breath and plow into it. Here's what our domain looks like. Recall. Get rid of this mess. So first, we've got the interior. Then we're going to have 4 separate edges, and then we're going to have 4 corners. Okay. All right. Let's see here. Where are we? Yeah. Okay, so let's start with the interior. This gradient is that. Set that equal to 0. You get this point, 1/2 comma 0, which is not in the interior, and so it does not count as an interior critical point. So throw it away. Everybody good? By the way, it is going to end up being a critical point on the appropriate edge. But it's not an interior critical point because it's not in the interior, so don't take it here. Alrighty. Now, look, why were we scared of this unit square? We were scared of this unit square because, oh my gosh, there's 9 separate subdomains, right? Yikes. Oh my gosh. But the thing is, yeah, there are 9, but look how easy the interior was to deal with, right? So it's 9 really easy little problems very often. So it's nothing to be scared of particularly. It's just, you got to have the courage to press forward and keep going, and yeah, it just all works out. Okay, moving along. Let's look at one of those edges. We're going to look at that top edge. The constraint on that top edge is y equals 1. Right? So here then is the function that is our constraint function, y minus 1. That's the thing that has to be 0. And that function has a very simple little constraint gradient. Degeneracy is clearly not a problem. That constraint gradient's never 0. Your Lagrange condition is easy to write down. The Lagrange condition, don't forget to combine that with the constraint itself. And here we go. Here we have our 3 equations and 3 unknowns. And I just have to solve those 3 equations and 3 unknowns. And look how easy, right? This is it's just freebie. In fact, even y is right there. And x is really easy to write down. Right? So that algebra was just no problem. And we have a critical point. In fact, notice it's the same critical point. It's the same as what we thought we had, but then had to throw away because it wasn't in the interior. Here it is a actual critical point on the top edge, yeah.
Why in the first one did you, once you found out that it's not in the domain, you got a point from the element?
Yeah, so why didn't I take this at that time? You're talking about while I was considering the interior? Yeah, so the point is because I was considering the interior. The interior, we're viewing our total domain as being made up of separate subdomains, right? The interior is the open inside of the square. It does not include the edges, right? Now, if the absolute maximizer that we're looking for, if it's on that top edge, if it is, then it will show up as a critical point on that top edge, right? So there's a tendency to say, look, I found something. This is I got to keep it because it might be valuable, right? Well, don't sacrifice the legitimacy of your argument because you're scared that you might not find it again at the appropriate time, right? So our argument that we're making here is that we're going to look at the critical points on the individual separate pieces. We're going to consider these as 9 separate little problems. And as a separate problem, looking just at the interior, that point is not part of that subdomain. And it's just not part of what we're looking at here. And if you get too sort of flexible, right, then your argument breaks down and it's not clear what your argument actually even is anymore. Is that cool? Does that make sense? So, and notice how, as promised, it felt bad to throw this away, but then it showed right back up. At the appropriate time. This point here is on the top edge. I'll say it again. If it were a critical point, if it were a maximizer, it would show up as a critical point on the top edge, and it did. So it's nothing to worry about. Great question. Anybody else? Okay. Again, not that bad. Right? I mean, sure, there's 9 pieces, but this one, it's just, you just got to write down what the appropriate conditions are, and you write it down, and it jumps in your lap, and boom, you're done, and you move on to the next one. Right? So let me not go through all 9 of these, but there is a right edge, and a bottom edge, and a left edge, and notice all of these, the algebra, it's just not that bad. Right? And they break down pretty straightforward. Okay. However, let's talk about the vertices. There's 4 of them, and each of these vertices is on 2 edges. You might say for each one of these vertices there are 2 constraints, and we could go into this long and involved conversation about, do we need to check for degeneracy and blah, blah, blah. Go through this whole rigmarole to try to find critical points on a set consisting of 1 point. Right? But how about this? My inner laziness has an idea. My inner laziness says, let's just go ahead and check it anyway. And then I don't have to go through that whole Lagrange argument. It's just 1 point. Right? In fact, here we are again kind of at the situation we were in Calc 1. In Calc 1, we were doing optimization. We had 2 endpoints. We didn't go through some sophisticated process in the hopes that I might rule out one of those 2 endpoints. There's just 2 of them. Just check them. Right? It's a lot easier. So that's the argument I'm going to make here. By the way, it turns out if you did want to really take this seriously, let's look at each one of these individually and let's find, is V1 thought of as a point in that set V1 with 2 constraints? If you go through the Lagrange story, it will be a critical point. All of them will be. They always will be. Vertices will always be critical points. There's kind of no way around it, as it turns out. So anyway, the point is, you don't have to make that argument because you don't need the argument. Just go ahead and check them anyway. So here's what it all breaks down to then. There are 2 edge critical points. There are 4 vertices critical points. There were no interior critical points. Put all those critical points into the same bucket. There's all of our critical points over the entire domain. Plug into the function. These are the values. Where is the function the biggest? Well, there and there. So these 2 points are the absolute maximum points. Everybody see how it goes? Not that bad, really. It's just slowly and patiently, and in fact, it's not even all that slowly. Okay. All right. Okay, so we're done with Chapter 4. Now, as previously discussed, we're going to jump back now into Chapter 6, and we were pretty much done with Chapter 6 anyway. But I do want to show you these last examples. 6.9 is, I call it computing line integrals and surface integrals. The idea is I'm just going to show you a bunch of examples of how to use all the ideas that we've seen in the previous sections to, do these computations. It's kind of no new ideas in this section, really. Okay. All right. Okay. Step 1. I like to call this diagnosis. So somebody comes to you with a question. It's probably me, by the way, but I come to you with a question of compute the following line integral. You have to, as I like to say, diagnose what kind of a problem is this? Is this a Stokes' curl theorem problem? Is this a fundamental theorem of line integrals problem? Is this a Chapter 5 problem? What do I do with this line integral that I've been given? Okay, so diagnose the problem. And there's a couple of steps in that. Step 1, figure out where you are in the diagram. I am such a big believer in these diagrams as a tool for students in solving these kinds of problems. So here we are in the R3 diagram. If I come to you and ask you for a line integral in R3, so over a curve that's in space, the vector field is a vector field in R3. That's where we are. That's what I'm asking you to compute. And the diagram tells you some free information. And that is that maybe the fundamental theorem of line integrals might be a candidate. Maybe Stokes' curl theorem might be a candidate. It also tells you Gauss's divergence theorem is not going to be a candidate. Look where it is. It's way over here. Right? So we're interested in this. Gauss's divergence theorem doesn't say anything about that. So don't even think about Gauss's divergence theorem. Now, related, triple integrals don't look good if the question is about a line integral, because it just couldn't possibly be relevant, right? So, make sure to sort of think that through. Keep in mind when you're taking a test, you're communicating thoughts. If you communicate the thought that you think maybe a triple integral might have something to do with the computation of this line integral, that's not a good thought. Right? So keep that in mind. Here's another thing. Looking at that line integral, this vector field, whatever that is, you should compute the curl of that probably. What you should not do with that vector field is compute the divergence of it. Right? Doesn't make any sense at all. Correction. In the using the tools and strategies that we've talked about here in Chapter 6, really in Math 212, there is no context, there is no precedence. Nothing we've done, none of the techniques we've discussed have anything to do with computing divergence of that vector field. That's the integrand for a line integral. So it doesn't. So not only will that not help you, it will be counterproductive in the sense that it takes you in a bad direction. And it makes you look like you're not understanding the strategy. Everybody on board? So no divergence, no triple integrals. Yeah. Okay. Okay, so we see our candidates. Now, next question. Can you actually use these theorems, and if so, which ones, or both? And, of course, there's always a possibility to be neither. All right, so let's go through these possibilities. Can you use the fundamental theorem of line integrals? Well, I would need for there to be an anti-gradient. That's what I would have to have. The way I wrote about this in the book is in order to be able to use the fundamental theorem of line integrals, I would have to go backwards through that arrow. Right? I have a vector field here. I would need to, from that, find this function over there. The gradient arrow goes to the right. I would need to go to the left. So I need to go backwards through that arrow. That's not something that is always possible. How do I decide if I can go backwards through that arrow? Well, we have a lifetime theorem down here that says take the curl. And if you get 0, then yes, there's an anti-gradient. Everybody on board? All right. So that's how you're going to decide if you can use the fundamental theorem of line integrals. Take the curl. Okay. Next question. Can I use Stokes' curl theorem? Well, by the way, let me observe while we're here. If you're going to use Stokes' curl theorem, again, you'd need to take the curl of the vector field. So I have a good bit of general advice, and that is when someone asks you about a line integral in R3, step one, just go ahead and compute the curl, right? See what that is. It's going to be useful in either of the two either of the two hopeful cases of being able to use one or the other of these theorems. It'll either tell you that there is an anti-gradient that you can go out and find, or it will tell you what the integrand is for using Stokes' theorem. So I say go ahead and do it. Line integral in R3, compute the curl. Okay. All right, but that's not the only question. If you want to use Stokes' curl theorem to compute this line integral, notice we will also need to we need to find the surface, that'll be the domain for our surface integral. Said differently, we need to find the anti-boundary, I like to call it, or said as I wrote it in the book, you'll need to move backwards through this arrow. The boundary arrow goes that way. If you say boundary, that means I give you a surface, out comes a curve. We need to take that curve and see, can we work backwards to find a corresponding surface. So that's why I like to use the term anti-boundary. Okay. And that's not always possible. The good news about this is you don't really need a fancy theorem. Curves, if you understand what the curve looks like, think about what it looks like, think about the picture, and just see the geometry and decide if there is or is not a surface. Does that make sense? Okay. So those are the two questions to ask. Is there an anti-gradient? That resolves whether you can use the fundamental theorem of line integrals. is there an anti-boundary? That resolves whether you can use Stokes' curl theorem. And then with those questions answered, you know what your options are on how to proceed with the question. Okay. So sometimes it may work out that that doesn't work. There is no anti-boundary, but there is. You took the curl, you got 0. There is therefore an anti-gradient. You can use the fundamental theorem of line integrals. If this is how it plays out for a given question that you might see on the final or whatever, you've just diagnosed this is a fundamental theorem of line integrals question, probably. Everybody on board? All right. Now, there is another possibility. It is also possible, by virtue of the curl being 0, it may be that it's a path independence question. Because path independence is another thing that comes along for the ride if there is an anti-gradient. Now, which one do you choose? Unless there's something really stopping you from finding the anti-gradient, I think fundamental theorem of line integrals is probably easier. So most of the time, I would think fundamental theorem. But path independence is a possibility. Okay. If you take the curl, it's not 0. There is no anti-gradient. The fundamental theorem of line integrals doesn't work, but there is an anti-boundary surface. Stokes' curl theorem is on the table. Well, again, you've just diagnosed what kind of a problem this is. I mean, I suppose brute force Chapter 5 plug and chug is always on the table, right? But very likely this is worth considering, at least, doing it with Stokes' theorem. And you've already got the curl. You already know what your integrand is there, right? You already know what that anti-boundary surface is. And so you've got a candidate alternative integral to consider computing. Everybody on board? Okay. I'm going to take this opportunity to again point out, look how the diagram helps us figure out our options, right? It tells you what your candidate theorems are. It tells you what operator to apply. It's just all of the ideas that we've talked about in Chapter 6, they're all organized on this one diagram. It's super, super handy. I'll remind you, I encourage you to memorize the entire diagram. Further remind you, I don't think it's anywhere near as hard as it sounds. In fact, you may have inadvertently, accidentally already memorized it, as we previously discussed. If you haven't accidentally memorized it, I encourage you to deliberately memorize it. I think it's very valuable. Okay, so that's that. Let's start working problems. So real quick before we work problems, note I've got this kind of summarized as a strategy for how to proceed when you're computing line integrals and surface integrals. Step 1, figure out where you are. Step 2, apply the operator that the diagram tells you to apply. That will resolve whether or not you can use the boundary theorem on the left of where you are. Looking at the domain and thinking about a possible anti-boundary tells you if you can use the boundary theorem on your right of where you are. Reminder, if the result is 0 in the operator, you can use the boundary theorem on the left, or you can also use what I'll call domain independence. So path independence if you're looking for a line integral, surface independence if you're looking for a flux. Right? And if neither of these happens, I wanted to leave that there. If neither of these happens, then Chapter 5 techniques. Right. And quick reminder, Chapter 5 techniques, the big Chapter 5 technique is parameterize that surface or curve, whichever the case may be. Parameterize it And the parameterization is the thing that allows you to do your pullbacks, right? But parameterize and pullback is the big strategy. But don't forget, keep your eyes open, keep your head on a swivel, look for the possibilities of geometric good fortune, right? Sometimes the dot product that you're interested in is obviously zero without even doing a computation, right? Sometimes for the integral that you're interested in, the entire domain is on the plane where y equals 7. Go ahead and stick y equals 7 right there inside your question. Things sometimes will simplify really nicely. So it's not just parameterize and pullback. Keep in mind the lucky breaks. Always be on the lookout for the lucky breaks if you're doing a Chapter 5 approach also. Okay, so there's our strategy. Now all I have left is a bunch of examples. I do see that it's about 11 o'clock, so I'm going to suggest we take our break now, and then I'll go through and show you all these examples. And okay. So see y'all in let's say at 11:15. See you then.